I'm going to spend a couple videos going over the content on vectors from 11.2, 3, and 4 in the book, and I'm really just going to hit some of the highlights. And as a refresher, remember a vector is a quantity that contains a magnitude, which is a length, and a direction. We can represent a vector geometrically by just drawing it, which looks like an array, kind of like these down here, or we can write them algebraically. In component form, we usually use these sideways V's on the side. And then we also, when it is printed, so like in this box right here, if it's bold, then that indicates that it's a vector, okay? Theorem A is from page 563, has some properties about vectors and scalars. So anything that is italicized here, these variables like A and B, those are scalars, meaning like just a coefficient, basically, is how you can think of that. And then anything that is bold is a vector. So read through this, make sure you understand this. Remember that the double absolute value bars like this indicates the magnitude or the length of a vector. Also notice that even though this is a 0, it is bold, so that's the 0 vector. And the 0 vector is in 2 dimensions would just be 0, 0, or in 3 dimensions it would be 0, 0, 0, etc. Okay? All right, so we're going to go through an example here using an algebraic representation. So vector A has a tail at 3, -2, 7, and a head at -1, 4, 5. So those are ordered pairs, or ordered triples, sorry. First, we want to find the component form. Then we're going to find the magnitude, and then write another vector represented here in terms of vector A. Okay, so first thing is, if we are writing a vector that is going from, I'm looking at the x coordinates first, from 3 to -1, that means we are subtracting 4. So the first component is -4. And then for the y points, we're going from -2 to 4, meaning we are adding 6. And then for z, we are going from 7 to 5, meaning we are subtracting 2. So vector A is -4, 6, 2. In component form, and it doesn't really matter where this is. We do have an initial and a terminal point, or a tail and a head, but this represents vector A, okay? And so that's the component form. And then for the magnitude, remember we're finding the length, so we're really just using the distance formula. Okay, so that's going to be the square root of each of these terms squared and then the sum. So that's going to be 16 plus 36 plus, thought that was a 27 for a second, plus 4, which is root 56, which we can stop there, or that's 2 root 14 if you would like to simplify. And sorry for all the clicking in the background. That would be my dog walking around, and she really needs her nails cut. Okay, and then the last thing is we want to write another vector that goes from this ordered triple to this ordered triple in terms of vector A. So let's go ahead and write the component form for that vector, and we'll call that B. So we can name it here. From 6 to 14 is a positive 8. And then from 0 to -12 means we are subtracting 12. And then from -3 to 1 means we are adding 4. And then if we compare this to this, we see that this is a scalar multiple of this. And it's actually -2 times the vector here, -4, 6, -2. Okay, so -2 times -4 is 8, -2 times 6 is -12, -2 times -2 is 4. Okay, so that means that this second vector, vector B, is -2 as a scalar or a coefficient times vector A. Okay? All right, and then for this next one, here's a pretty common application. Let me see if I can move this down. Of vectors. Okay, and it does happen to be one of the few instances where we are going to use degrees. So the setup here is that we have a weight that is being suspended by 2 wires. So you can think of the weight being right here. Whoops. or even down here, it doesn't matter, but we've got gravity is pulling the weight down, okay? And it's 200 newtons, and it's supported by these two wires. And then we also have, these are the angles inside here that represent the angle of those wires. Because it is being supported, in other words, it's not being pulled up or pulled down or left or right, that means we have equilibrium. And really we're looking for the magnitude of the tension in each wire. There's some extra, physics vocab terms here, but really what we should just be thinking about is solving right triangle, trigonometry, like basic SOHCAHTOA stuff, okay? But we're using vectors to represent the wires and the forces, okay? So what I'm going to do is I'm going to label these three vectors. So this wire I'm going to call U, this one I'm going to call V, and then this one I'm going to call W. And we do know that the magnitude or the amount of the force pulling down is, so magnitude of W is 200 newtons, okay? And then we've got these angles, and that we also know because the weight is not moving, or because, the ceiling or whatever it's suspended from is not falling, then we have a balance vertically and a balance horizontally, okay? So let's think about these as two right triangles, okay? And they've got a 33-degree angle inside there, and then the 50-degree angle inside here. Okay, and because they are balanced, then that means the sum of the horizontal pole and the sum of the vertical poles should be 0. Okay, so to represent that, and again, I'm just using SOHCAHTOA. Okay, I know that cosine of this angle right here is going to be equal to this side over the hypotenuse, which is vector U, okay? So that means I can write the magnitude of U times cosine of 33, okay? Which is going to represent the horizontal tension this way. This has to be equal to the horizontal tension to the right. So I can set this equal to the magnitude of V, which think of that as the hypotenuse of this triangle, times cosine of 50, okay? So this is showing a balance horizontally, and then vertically, we know that this force plus this one has to be equal to this one because it's not moving, the weight is not moving up or down, okay? So using some more trig, we can say the magnitude of U times sine of 33 plus the magnitude of V times sine of 50, so that's this side of the triangle plus this side of the triangle, has to be equal to, and then this is coming just straight down, so 200, okay? And then we have a system of two equations and two variables, so just doing some algebra here. I'm going to take the first equation and divide everything by cosine 33, so we end up with the magnitude of U is equal to the magnitude of V times cosine of 50 over cosine of 33, and then we can plug that into this equation, into the second equation, so we get the magnitude of V times sine 33 times cosine 33 over, cosine 50, over cosine 33 plus magnitude of V times sine of 50 is 200. At this point, factor out the magnitude of V, and so we'd have all of this plus all of this, and then divide both 200 by that sum, and we get, go ahead and do this, we get 168.994 newtons. Okay, and then we can plug that back into this equation and get that the magnitude of the tension in the, vector U, or in the other wire, is about 129.52 newtons.